Okay, welcome back everybody. Today we're going to do a full tutorial on how to troubleshoot an S17Pro board that has a partial number of ASICs detected. Okay, so I already did some preliminary tests with this one. I know, or I think it's going to be a good candidate. So let's go ahead and look at that together. And we're going to do, like I said, a step-by-step. So if you're a total beginner, hopefully you find all the information you have here, or you need here, to be able to troubleshoot the S17Pro board specifically. So here's what you're going to need. You're going to need your board to troubleshoot, obviously. You're going to need some sort of tester. I'm using this one, but you can also use like a universal one. You're going to need a multimeter. Doesn't matter really the brand or the model or whatever. And you're going to need a bench power supply set to 21 volts roughly. All right. Okay. Now let me just focus a little bit better on this so that you guys can see. All right. So first thing first, when we diagnose a board, we want to make sure we can put power to it, right? So we look, visually, make sure that everything's good, that the heat sinks are not touching. That's the main thing usually. And we look for any signs of something going catastrophically wrong, which is not the case here. Okay. And then I got my two positive and negative coming from my power supply. And now you want to make sure that you connect those the right way, because if you connect them opposite, then you will burn more stuff. So on the S17Pro boards, you have the data cable that's going to your tester, then the post next to it is your negative, so you take your black one, you put it there, and then of course the third one, the one that's on the edge of the board, is your positive. So put that there. Now you may see a little spark when you connect that one, or when you finish connecting the two connections. That one didn't really do it, but that is normal. Don't worry about it. It's just those capacitors charging, so they are short-circuited for a short period of time, but again, totally normal. Okay, so first thing first we do, just fire up the tester. And again, in my case, I'm using this one, but not very clear. Let me do that camera again. Okay, so I changed the camera angle to really focus on the tester. So if we start the tester again, as you saw previously, so we got 41. And then I usually stop the test right away so that the board doesn't get too hot. But so if you're using like a universal fixture, the Asian one, either like if it's a Zeus tester or like a generic AliExpress ones or whatever, so then you would just push the green button and wait for the result to happen. On the S17Pro board, it's only a few seconds usually, and then it's going to give you that same number. Okay, so we know we got a partial number of ASICs detected, right? 41. So what we need to do now is confirm if the problem is really in the 41, 42 area, or if it's somewhere else on the chain. So if you don't know, on the S17Pro boards, this is chip number 1, and then it goes down and then up in the second domain, and then over and down in the third domain, and then up in the fourth, and so on and so forth, right? It snakes back and forth. So if we look at number 41, so that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 times 4, that's 36. Sorry, this way, 36, 37, 38, 39, 40, and 41. So this is chip number 40, and this is number 41. And so this is 42. So this is our area that we're going to be focusing on. Okay, so let's go to the microscope. Let's, so keep that in mind. So we're going to be looking at those two chips right here at the top of the domain. This is what I call the top, but just because that's the way I have the board position. So this is 40, this is 41. So microscope. All right. Let me just get you guys positioned. Struggling a little bit. Okay, so the chip you see on the right is chip number 40, and the chip you see on the left is chip number 41. So what we want to do now is use our tester cables, our little jumper. So if we go back to the overhead for a second, so I have these jumper cables, which is really just a pair of multimeter needle probes that I put an alligator clip jumper wire in between. So these two are connected together, and that's what we're going to use to take some voltage from somewhere and put it somewhere else. Okay, so back on the microscope, the idea, if we want to shorten the chain, shorten it up to 40, so we want to cut everything that is 41 and after, we need to inject 1.8 volts into the RI, which means the input, the RI of chip number 40, right? So if I want to test up to 40, and you see this is 40 and you see the traces that go around up to 41, so I want to basically cut the chain right here and test all this first part up to 40. So I need to inject 1.8 volt into the RI of 40, all right? Now, without taking the heat sinks off, because we want to do that, that's a pain in the butt. So I know by experience that this middle test point right here is the RI of chip number 40, okay? And so now the question is, for the 1.8 volt, do I take the 1.8 volt out of that domain, or do I take the 1.8 volt out of that domain? And the answer is, when you're testing the last chip in a domain, so 40 is the last chip in this domain before it switches over to 41, right? So when you test the last chip in a domain, you always want to take the 1.8 volt of the next domain over. So I need to take the 1.8 volt into this domain where 41 is, and then inject it on this test point. I'm using this test point because it's convenient, but you know, if you follow the trace, then you'll see that you can also use, you know, this top left pin or this resistor right here or whatever works for you, but I like using this test points because it's nice and open, there's no other component around, so that's nice. Okay, so let's move on to this. So this is number 41, as we said, and this is where I usually take my 1.8 volt. So we know that these two capacitors here are between, on the right side, the two on the right side, are between the ground, which is this big copper trace, and the 1.8 volt, which is this other trace on the left side. So all I need to do is take one of my probe, and maybe I'll zoom in so you guys can really see. There we go. So I need to take my probe, and I will make sure I get a good contact. And if I put just a little bit of pressure, you see I made like an indent in the solder, and so that's gonna make my probe rest in there more easily. If I can get, there you go. Okay, and then with that probe I want to make sure I'm not touching anything else, okay? So I want to make sure I'm not touching the 0.8 volt capacitors that are behind it, or any of the heat sinks, or anything like that. So let's go back to the top of our domain. Oops, and my probe slipped, so let me just put this back. Okay, so now that we are back and we're looking at our test point where we need to inject it, so what we're going to do now is fire up the tester and put our 1.8 volt in the test point. So now we see we got 40, so that is what we are expecting, right? So we cut the chain after number 40, which is where this test point is. We cut the chain after number 40. So we are testing from chip number 1 to chip number 40. And the tester is saying 40 chips. And it was like a solid 40 chips. So if you get anything other than 40, then it means that your problem is somewhere else in the chain. It's somewhere between 1 and 40, okay? But now that was solid, so that's what we want to see. Okay, so now we're gonna test after 41. And to be honest, it's probably not required, but it's always a good thing to do just to make sure that your data is consistent with the problem that you're seeing. So now I am on this domain. So again, right there is chip number 41. And now I'm looking between 41 and 42. And I can do, I'm just a little bit out of focus here for myself. There we go. And so now you're wondering, well, what is the RO point into these, right? And so you see those two diagonal test points. So this one up here and this one at the bottom here that are kind of diagonally. So one of those is the RI of chip number 41. And how you know which one is which. So if we go all the way to the other edge of the board, some domains have a mode 0 written, right? And then the other domain, which would be right here, doesn't. And then it alternates, right? So mode 0, and this would be a mode 1. Mode 0, and so on and so forth. So if we go back to our domain, which is this one, we see that we got a mode 0. So we know that all of these chips, so from 41 to 45, are on a mode 0 domain. And on a mode 0, we know that the RI is the bottom test points of the two. Okay, so this is this one I'm touching right here. Now, if we were on a mode 1 domain, like the one right next to it, let's not take the one that's on the edge of the board, let's take this one. So, a bit hard to see, but here are your two diagonal test point, right? So we know we have this top one and this bottom one. And because this is a mode 1 domain, then the RI would be the top. So mode 1, RI is the top one. Mode 0, like the one we're interested in, RI is the bottom one. So that's how I remember it. And so what I'm going to do now, I'm going to put one of my probe in that test point. I'm going to put my other probe on that same 1.8 volt. And then I'm going to fire up the test, and then it should say 41. It should say like a solid 41, right? So again, no change there. So that's good. And now, just for kicks, we're going to look at trying to test 42. So again, this is chip number 42. So when we are looking between 42 and 43, we are again on a mode 0 domain because we haven't changed domain. So we know that the RI is this bottom test point. And then I'm going to fire up the tester and touch the 1.8 with my other probe. And I still got 41. Okay? So this is all the testing really that we need to do to figure out where the break is in the chain. So that's usually the first step, right? You figure out where the break is, and then you can figure out what is the thing that is broken. Okay? So quick recap. So okay, so this is 40. So we cut the chain between 40 and 41 up here just to make sure that our 41st chips were stable, and then the tester was at a solid 40. So we know we are good up to 40. Then we tested 41. We had 41. Again, solid and stable, so that's good. So we tested between the two here, between 41 and 42. So we cut that here to test up to 41. And then we cut between 42 and 43 to test up to 42. And then the tester was still showing 41. So chances are there is a problem between 41 and 42. Okay, and so this is the time where I would usually remove the heat sinks and just have a further look. Okay, so let's do that. Let me get my air. Okay, so again, make sure we are removing the right ones. So this is 41. So what I do is I just shoot the air sideways on the heatsink and I tap it gently. And when I see it start to move, which should happen shortly. There we go. So when I see it start to move, just grab it, pull it straight up. And we're going to do the same with 42. And so you might be wondering, why are we looking at 41 and 42? Because, so we know 42 technically is the problem. However, we don't know if it's the problem because 42 itself has a problem, or we don't know if it's not being detected because 41 is not providing the right signals to 42, right? If that makes any sense. Okay, so let's move over. Actually, let's go to the microscope first and see what we got. So I think it's fairly obvious, or you know, it's so this is your 42, which doesn't look like there's a whole lot of copper left on it, and this is 41. It also shows some signs of being a little tired, but overall looks in better shape than 42. So anyway, so now we need to have a look at the signals between, just zoom out. Okay, this is as far out as I can zoom, unfortunately, but let's have a look at the signals between 41 and 42 and see what we can see. Okay, so I got my two probes. So these are not my test jumper. These are the probes from the multimeter. So I put my multimeter on volts, obviously, right? It's on volts. And now what I'm gonna do before I fire up the test, so I'm gonna take the ground on a chip, so any ground in that domain can do, and then we're gonna look at our different signals, right? So I know that, you know, by experience, I know that this resistor has the clock. Let me just make sure, let's zoom in a bit. So my ground probe is on the top of the chip, could be on top of any chip of that domain, while assuming there's still some copper left, unlike that second chip. But so I know that this resistor is the clock. So we know that this one is the RI, as we talked about earlier. I know that the other one out of those two diagonals is the CI. This trace right here that ends up just on one side of the resistor, that's the reset. And then this guy, I believe, is the BI, right? So let's fire up the test and see what we can see. So you're seeing the multimeter, I'm seeing the multimeter. So I'm gonna make sure I'm only touching one thing. So I got about 1 volt for the clock on the multimeter, which is okay. So I get a RI of 1.8 for RI, so that's actually good. CI is 1.8, that is also good. Reset is 1.8, that is good. And BI is close to 0, which is also good. Okay, so based on that, we know that all of our signals are okay. Now I'm also going to look at my 1.8, which I do have, and my 0.8 on the other capacitors, which is also good. Okay, so everything going into chip 42 should be good. So now let's look at the output of chip 42. Okay, so now the board's getting a little hot, so I'm gonna have to move a little bit more quickly, but so here's our clock, which is nothing. Here's our CI 1.8, that's good. RO 1.8, that's good. Reset 1.8, that's good. And BI close to 0, that's good. So that chip is not passing clock. As you can see right now, I got nothing for, I'm going to stop the test because the board is getting hot, but yeah, so the test is off right now, but it was not passing clock, right? We had like almost 0 volts on this. So actually, let me fire the test again, and I'm going to make sure that it's not our resistor that's the problem. Nope, same thing. Okay. So see what I did there? So I measured after the resistor, so this pin, which is pin number 8, is going through this resistor, and I use this test point, but if this resistor was bad, then there's a chance that it could cut the signal. So I measured on the chip side and then found still 0 volt or very close to it. So if we recap, we had all our signals were fine going into 42, but we did not have a clock coming out of 42, despite having the 0.8 and the 1.8 volt being fed to it. So other things that we could check that we don't technically need to because we know they work, but so let me fire up the test again. So domain voltage, between the voltage that we are, between the domain that we are looking at and the ones next to it. So we got both, right? So between second to last domain and the one before, and between second to last domain and the one after. So that's good. But again, we knew that that was good because chip number 41 was powered on. So we didn't really need to check that, but it's always a good thing to check. So based on that, based on the fact that clock has all the signals going in, all the power is going to it, but somehow is not passing the clock forward, and also based on visually how that chip looks, then I feel like it's a pretty easy call to call that chip bad, right? And so we're gonna go ahead and replace the chip. Okay, here we are under the microscope. So we got our chip number 42. First thing we need to do is clean up a bit around it, just so all the stuff that's around it doesn't end up in our flux and potentially cause problems when we go to put in our new chip. But as you can see, this looks disgusting. There's not a whole lot left on the top of the chip. I'm just going to zoom out a bit because I like having a little bit wider field of view when I do that. Okay, so I got a new chip ready here. So the idea is that I'm going to heat up the board, take that old chip off and put the new chip on. Alright, let's do it. I'm going to put just a little bit of flux on the sides. That's all we need. Got my tweezers, so let's fire up the air. So I'm using 340 degrees, 60% air from the bottom. And you will see that it melts the flux really quickly. So now I'm just waiting for the pins to get shiny, because then we know they're going to be liquid. Not quite there yet. Alright. Nope, not yet. There we go. Now we're fairly loose. I'm just going to wait a couple more seconds. Okay, so when I want to pick up the chip, what I'm going to do in order to make sure that I leave enough solder on the board, so I grab the chip and I just rotate it, and then when I get to the last pin, then I can pull it up. And so what that does, that makes sure that the surface tension has a chance to keep enough solder on the board, so that you don't have to mess with you know, adding solder or whatever. And so I'm just going here, tweak the angle of my chip a little bit. That's too much. There we go. So I'm gonna line it up. So all my pins are liquid, I think. And then I am going to drop that on there. Then I'm going to gently tap it, just to kind of help it find its home. And it's pretty solid now, so we're going to, I think I'm just a little bit too much on one side. It's hard to tell. Okay, I'm going to leave it. Don't mess with it. Cut the air. And we're going to see what we got. Okay, so the board has cooled down. We got our chip here, a new chip. So first things first, we're going to do a little bit of cleanup, make sure we... So then we're gonna move on to testing. What do you guys think? Hopefully that was our only problem. So again, we got data cable, then negative, then positive. Little spark is good. And come on. 48. So that is all of our chips. So personally, at this time, I would call this board fixed. So what I would do is I'm gonna put the heat sinks back on, obviously, in a second. But after that, I'm gonna throw that in a miner and have it hash for probably like 24 hours, just to make sure it doesn't have, excuse me, any issues before I give it back to the customer. If this was my personal board, then of course I would just throw it in there and hope for the best, basically. But if you're using the universal tester or fixture, then your next step is to do a hash test. So I don't have to do that because the tester I have doesn't actually touch the EEPROM data, but the universal type tester does. So what you need to do, if you're using a universal type tester, put the heat sinks back on also, throw that in the miner, and then with your test fixture, have it do the hash test. So it's gonna do the same thing for the first couple of seconds, detect all the chips, and then it's gonna move on to a hash test. So the board is actually gonna be hashing and getting hot, and so that's why you need to make sure that you have it ideally in a miner case with the proper cooling fans. You know, if you wanna like build your own little cooling setup, it's also possible, but I'm gonna recommend that right now. The best way to do it is really just to put it in the actual miner case, hook up the fans to your test fixture. That's important, so that the tester can spool up the fans, and just let it do its thing. And then it's gonna test different frequencies and different voltages, and if the board or if all the chips are responding properly and working properly, then eventually your board is gonna pass the test at a certain level. So level 1 is the best level, so that would be like the highest frequency and the lowest voltage. And then it goes down to, I think for the Pro, I think there's only 2 levels, but for some other models, I'm thinking the S17 Plus, I think there's like up to 9 maybe, 6 or 9, something like that. Anyway, and ultimately, that is what you are seeing on the board. Just in case you didn't know, there is a level sticker on the board. So this one is level 1. So if I was to throw that in a universal test fixture and do a hash test, then it would most likely pass at level 1. Alright, so let's put some heat sinks back on, and we are going to call that a day for that one. So I also want to make sure that the bottom of your heatsink is not dirty, especially if it came off a chip that had that got its copper ripped off. Then maybe you could have some residue on the bottom of the heatsink. So what I do now, I just heat it sideways with my air wand, and then when it gets hot enough, I just gently scrape it. And I try not to get solder all over the heatsink, because then that solder can end up on your pins. There you go, good for that one. And let's look at the bigger one. There's a little bit of crap on there. Sorry, I'm just slowly moving on the frame here. There we go, a little bit of dust, a little bit of whatever that is. And then, gonna make sure we put the right heatsink at the right place. So I heat it up. And then line it up. Keep heating it. And then when you feel that it's sitting flush on the chip, then you take the air off. Just hold it there for a little bit. You can blow on it to make it cool faster. And there we go. And so after that, you do the wiggle test. So I take my needle nose, I put it on the center part of the heatsink and just wiggle it back and forth a couple times. Make sure it won't come off. And if it does, then it's not a big deal, but you, well, if it does come off now, it's not a big deal, because you get to just try again and put it on. But if it does come off when it's in the miner, then that's obviously a much bigger problem. And that could cause some really big issues as far as short circuits and melting PCBs and whatnot. So just want to make sure we do a good job. Again, I line it up, try to make it straight, as if we were never here. There we go. Wiggle test, that's good. Turn off the air. Okay, so now the board is a little hot, obviously, because I just blasted it with a bunch of hot air, but what I'm going to do is let that cool down one more time, test it one more time. I won't do that on video because it's just formalities, really, but hopefully I get 48 chips again, and if I don't, then I know that something with those two heat sinks is wrong, so I would take them off again and look if I, like a solder ball dropped on the pins or something like that, but chances are you'll get all your chips again and you can go from there. Yeah, so hopefully you guys got something out of it. So I just realized that I did not turn on my microscope camera when I was on a microscope, so sorry about that, but you didn't miss much really. I just cleaned the chip, the flux, and that was it really. Looked at the solder job. Anyway, so yeah, I hope you got something out of this. You know, so step one of any troubleshooting is you figure out where the problem is. Step two, you figure out what the problem is, and you fix it. So easy peasy, 3-step. And it's hard to do a video, you know, covering every possible scenario because all the boards are different, but I would say that chip issues like this one had is really probably going to be like 95% of the issues that the boards have. So, you know, there can always be some like power issues and some control issues maybe, but those are a lot more rare, and if I do come across them, I'll make a video on them for sure. But this should hopefully show you how to test the chain from chip number 1 to chip whatever, and from there you can see, you know, if the problem area is after or before the area that you're shorting out, and based on that you can quickly isolate where the problem is. And once you know that, then you look at the chips themselves, look at the signals, look at the powers, so both domain voltage as well as the 1.8 and the 0.8 volt. If all of that is there, if all the signals are there, if all the powers are there, then assume bad chip, really. So that is it. Thank you very much. If you got any comments or questions, either leave them in the comments below or come find me on Discord, and I'll be able or really happy to talk about it. Thanks a lot.